Good morning, gentlefolk. Sorry, I got a little bit of stuff I'm taking care of this morning. Today we're going to continue talking about infinite series. I will give you your first few convergence tests. Kind of remind you what we've been doing this week. And then the big take home for today is going to be what's called the integral test. So we're getting started about 15 minutes late, so I hope you can forgive me. I am going to go about 15 minutes past our normal stopping time. Zoom out, zoom out, zoom out. So this is Calc 2, today is the 10th. The big one today, oh, come on, focus, you fuck. Big one today is the integral test, which is your second convergence test for infinite series. So I want to remind you in your notes, I strongly advise you to have a page for theorems and convergence tests for improper integrals, a separate page for theorems and convergence tests for sequences, and then a separate page for theorems and convergence tests for infinite series. You'll have your regular notes where you write down all the shit that I write here, but then after that, you need to compile the important bits into localized chunks, because you need to have one place where you can look back and go, oh yeah, these are the tests, these are the theorems. If you don't, you will get confused. The section number for this, I believe, is 11.3. Yeah, 11.3, integral test. All right, I want to remind you of a few things first, though. The rewrites for exam 1 are due today. So remember, you're allowed to rewrite just one question, one free response question from the test that either didn't go well for you or you were unable to get to during the test time. I'll grade those over the weekend and update your exam scores, and then the exam 1 scores will be finalized, no more changes. There are 2 homeworks that you should have been working on recently, homework 7 and homework 8. Each day I've been going in and clearing out the extension request. So hopefully your homework 7 is done or very, very close to being done, and you've been working on homework 8. Homework 8 is due on Monday. It is a somewhat long homework set, just like homework 7. Remember, you are in the thick of it now. You are balls deep in Calc 2. This is the hard stuff. So be ready to work hard. This is a hard class. This is the hard part of the hard class. So grind time, right? Put your nose to the stone, just work. Work. Several hours a day, every day, must be done. If you do that, you will be okay. If you do not, it will not be okay. I want you all to be okay. So please work hard, right? Several hours a day on homework. That's it. We're getting close to exam 2. Remember, exam 2 will be the week of the 20th. Which day that week the test will take place, I'm not sure yet. It depends on how quickly we move through the material. So let's get started, okay? Last time we talked about the test for divergence. Which I abbreviate TFD. And this is a convergence test for infinite series. It says, if the limit as n goes to infinity of an is not 0, then the series sigma an diverges. And that series might start at 0, it might start at 1, The theorem is true independent of this lower bound here. But yeah, that's our first test for convergence. If the general term of a series does not go to 0, then the series has no chance at converging. The only way for an infinite series to converge is if these guys, the ANs themselves, get real small real fast. And remember, the converse is not true. It is possible that lim n to infinity an equals 0 and the series sigma n from wherever to infinity an still diverges. So a test for divergence only works in one direction. If the ANs don't go to 0, then sigma an must diverge. If the ANs do go to 0, then the test is inconclusive. So, i.e., if lim n to infinity an equals 0, then TFD is inconclusive. Okay, it's very important that you remember that. It's a common true-false question on exam 2, hint, nudge, wink, whatever. If lim n to infinity an equals 0, then sigma an converges. Not true, not at all true. What is true is that if the lim as n goes to infinity of an is not 0, then sigma an diverges. That is true. But the converse, if you flip the logic in that sentence around, is not a true statement. We call this a one-way implication, right? If you give me a match, then I will burn down the building. However, if the building is burned down, you cannot assume that that means you gave me a match. The thing might have been struck by lightning, or maybe there was some faulty wiring, right? So it's a one-way implication. If this, then this, but it does not go back the other way. The new material for today, section 11.3, is on the integral test. And you may remember that I said an infinite series is a lot like a type 1 improper integral. The integral test tells us exactly how much like a type 1 improper integral the infinite series is. So here's the basic idea. If f of x is positive, continuous, and decreasing, then the integral from wherever, say a to infinity of f of x dx converges or diverges together with the infinite series sigma n from a to infinity f of n. That's the idea. So you can relate an improper integral to an infinite series. In practice, the way we use this is someone gives you the infinite series, you check that the corresponding function is positive, continuous, and decreasing, then compute this integral. If this integral converges, and this shit is true, then the series converges. If the integral diverges, and this shit is true, then the series diverges. That's the basic idea. This is going to let us prove a few interesting things. Right, so here, let me state the theorem exactly as it is. So theorem Remember, some sequences we can think of as dots along the graph of a continuous function. So here's the idea. If an is equal to f of n, where f of x is positive, continuous, and decreasing, then sigma n from wherever to infinity of an converges if and only if integral from a to infinity f of x dx converges. This is the way it's stated in your textbook. This is the way you should think of it. And it's really saying the same thing as the basic idea that I mentioned above. So this is called the integral test. In other words, in answer to the question in chat, said, how can we form a series out of a function? I thought we could just form series out of sequences. Remember what a sequence is. A sequence is a function whose domain is the natural numbers. So if you take a continuous function and you restrict its domain to whole numbers, that will give you a sequence. Yeah, no, good question. There's a picture that goes along with this. And basically, you can think of the infinite series as being like a Riemann sum for the integral. So maybe here's my sequence, A1, A2, A3, 4, 5, whatever. Remember, my infinite series is the area of these rectangles. All added up. Let's think about the graph of the continuous function that goes through those points. What do you notice about the integral? So the integral is the area under the curve. It's approximately the area in the rectangles. And depending on whether I shift left or shift right, there's some sneaky tricks I can do here. In particular, the area under the curve will be finite. So this says if the area under the curve is finite, then the area in the rectangles is finite. That's the basic idea here, right? So this is the theorem, and this is why the theorem works. Because I can think of the curve like this as being a right-hand Riemann sum for these rectangles, or I can think of these rectangles, sorry, as being a right-hand Riemann sum for the area under the curve. The area under the curve is a little bit bigger than the area in the rectangles. So if the area under the curve is finite, then so must be the area under the rectangles. On the other hand, if I swap things around and I build the left-hand side Riemann sum, then you'll see that the area of the rectangles looks a little bigger than the area under the curve. And so if the area in the rectangles is finite, then so is the area under the curve. So things go both ways. The positive, continuous, and decreasing stuff turns out to be what is necessary in order to get the if and only if. So you could throw away the continuous and decreasing requirement and still get one direction of the implication, but we want both directions. I don't want to get a whole lot more technical than this in the proof. If you want to see the technical details of the proof, the textbook actually does a really good job, right? You'll see here a very similar picture to the one I just drew for you. And then here's the shifted version of the left-hand Riemann sum. And they do the whole proof here, right? So if f is continuous, positive, and decreasing on the interval 1 to infinity, they use 1 for a, and an is the sequence that you get by restricting f of x to the integers, then this series converges if and only if this integral converges. In other words, if the integral converges, the series converges. And if the integral diverges, the series diverges. So how do we use this? Well, normally someone will hand you a series like this, and then you will find out what is the function f of x. You will check that it is continuous, positive, and decreasing, and then you'll compute that integral. They do have a few nice notes here. F does not need to always be decreasing. It needs to be eventually. They use the word ultimately here, but eventually decreasing. So let's play with this. This is your integral test. This needs to be your second thing on that page of convergence tests, right? So I said you should have a note, you should have a page in your notes dedicated to convergence tests for infinite series. This should be the second item on that page. The first one should be TFD, test for divergence. So these are your first two convergence tests for infinite series. Those two bracketed statements need to have special places in your notes. There will be several more, but for now, this is what we have. All right. So I want to investigate the convergence, i.e. determine whether the series converges or diverges, sigma n from 1 to infinity 1 over n squared plus 1. First, just to make sure that you remember what this sigma notation means, let's write down the first few terms of the series. It's 1 over 1 squared plus 1 plus 1 over 2 squared plus 1 plus 1 over 3 squared plus 1, and so on, forever and ever and ever. So that's 1/2 plus 1/5 plus 1/10, and on forever. That's what my infinite series is. And I want to know, does this converge or diverge? We can try TFD. Here, the limit as n goes to infinity of an is the limit as n goes to infinity of 1 over n squared plus 1, which is 1 over infinity plus 1, which is definitely 0. So what do we learn from TFD? Yeah, not a damn thing. This is inconclusive. Remember, TFD only ever tells us anything if the limit is not 0. If the limit of the ANs is not 0, then the series diverges. If the limit of the ANs is 0, we don't learn anything. You cannot conclude from this that the series converges. You can conclude nothing. So I go, okay, let's try the integral test. It's the only other tool I have right now besides trying to find a formula for the partial sums, and that's hard. So next we try the integral test. What is the function f of x that is relevant to this series based on the integral test? The sequence 1 over n squared plus 1 is the restriction of what positive continuous decreasing function? Not quite 1 over x. 1 over x would be related to 1 over n. So you just swap the n's for x's, that's all. So 1 over x squared plus 1. Right? If I only plug whole numbers into this, then I get this. So my function here, f of x, is 1 over x squared plus 1. You just swap the n's for x's. That's all. So then I need to check, is f positive, continuous, and decreasing? F of x is 1 over x squared plus 1 is positive because x squared plus 1 is positive, right? X squared is always greater than or equal to 0. So x squared plus 1 is always strictly greater than 0. And a number whose reciprocal is strictly greater than 0 is always strictly greater than 0. Continuous? Yes. Because x squared plus 1 equals 0 has no real solutions. Right? There is no number that will make the denominator 0. And that's the only way this thing could fail to be continuous, is if the denominator was 0. So he is continuous. Decreasing, two ways to do this. You can take the derivative and show that the derivative f primed is always positive. Or you can make this sneaky argument. 1 over x squared plus 1 is decreasing because x squared plus 1 is increasing. And where are we talking about? We have to be a little bit careful. We'd say on the interval 1 to infinity, because x squared plus 1 is increasing there, i.e. x squared plus 1 all primed is 2x, which is greater than 0 on the interval 1 to infinity. So the lazy man's way to show that a function is decreasing is to show that it's the reciprocal of an increasing function. Doesn't always work, but it works a lot for the type of functions we mess with in the integral test. An alternate way to show that this is a decreasing function would be to just take its derivative and show that the derivative of 1 over x squared plus 1 is always negative, at least as long as you're in this interval. Right? So this is the fast and sneaky way to verify the hypotheses of the integral test. And you'll want to get good at this, because this shit can be pretty time consuming if you aren't fast at it. So you see each of these has a little sneak, right? Instead of solving the inequality 1 over x squared plus 1 is greater than 0 to show that it's positive, I just make this little argument that, oh, it's the reciprocal of a positive function, therefore it must be positive. Continuous, instead of going through the definition of continuity for every real number, which you would run out of time because there's infinitely many real numbers, you just observe that the denominator is never 0. Oh, well, if the denominator is never 0, then this thing has to be continuous everywhere because it's a rational function. And then to get decreasing, this is 1 over something. So you might check that the something downstairs is increasing, and the reciprocal of an increasing function is always decreasing. So yeah, sneaky, fast ways to get these things. They're all things that you learned how to do in Calc 1. So if the sneaky, fast way doesn't jump out at you, you can always go back to your Calc 1 stuff and check using like number lines, definitions, and first derivatives that your function satisfies these hypotheses. But it takes time, so you want to get good at doing it fast. All right, since f of x is these things, the series sigma n from 1 to infinity 1 over n squared plus 1 will converge or diverge together with the integral 1 to infinity 1 over x squared plus 1 dx. So next I calculate this integral, or I figure out whether that integral is convergent or divergent. And then my series, I will know, does the same. So the integral from 1 to infinity 1 over x squared plus 1 dx is the limit as r goes to infinity, integral 1 to r, 1 over x squared plus 1 dx, which is the limit as r goes to infinity. I need an antiderivative for 1 over x squared plus 1. That's arctan. So this is the inverse tangent of x evaluated from 1 to r, which is the limit as r goes to infinity of arctan r minus arctan 1. And as r goes to infinity, arctan r goes to pi over 2, and the arctan of 1 is pi over 4. Pi over 2 minus pi over 4 is pi over 4. So the integral 1 to infinity 1 over x squared plus 1 dx converges. Therefore, by the integral test, the series sigma n from 1 to infinity 1 over n squared plus 1 must also converge. And that's it. So we said because the function you get by replacing the n's with x's is positive, continuous, and decreasing, the series 1 over n squared plus 1 summed from 1 to infinity, or sigma n equals 1 to infinity 1 over n squared plus 1, does the same thing as the integral from 1 to infinity 1 over x squared plus 1. The series and integral converge or diverge together. Then I compute the integral, and I find that the integral converges. Therefore, the series must also converge. That's the logical flow for the integral test, and you need to get comfy with not just the technical bits, but also the flow. A common question at this stage is, well, are these equal? In other words, I know that the integral converges to the value pi over 4. Does that mean that the series converges to pi over 4? And the answer to that is no. So the integral and the series do not have the same value. Naz asks, how did we get the inverse tangent of r equal to pi over 4? We didn't. This piece goes to pi over 2. And that's coming from the graph of the arctan function. So remember when we talked about this earlier, this is one of these important limits that you just need to know, right? You got to know what the graph of arctan looks like. I can show you here. This is something that bit a lot of people in the ass on the first test, is just not knowing graphs. So I'm glad that you remember. I'll remind everybody else, because if you're asking, I'm sure other people are wondering too. Here's arctan. And as x runs off to infinity, the graph approaches pi over 2, right? So as we wander way out here, you see that the limit as r goes to infinity of the inverse tangent of r is pi over 2. So this piece goes to pi over 2. This piece is pi over 4. So you get pi over 2 minus pi over 4. That's pi over 4. Okay, so because the integral has this finite value, the integral converges. And by the integral test, if the integral converges, so does the series. But the series is not equal to the integral. So the series is not equal to pi over 4. I don't know what the sum of this series is. It's not pi over 4. If you look in the textbook, they do go into a little bit more detail estimating the infinite series. There's their proof of the integral test. It's a good proof. You should go through it. But I'm not going to make you guys do that, right? So I'm not going to make you estimate the value of the series using this inequality from the integral test. I'm just concerned that you know how to use the integral test itself. But you should read the textbook. If you haven't read the textbook, you should. Definitely check out section 11.3. Their proof of the integral test is good. It's actually a good proof for this class. It's a proof that when I teach this class in person, I go over it. But I don't want to lose you guys in the details of the proof. So I will encourage you to read the proof here. It's not too bad. And if you're curious about any steps or if you have problems with any steps, come talk to me and I'll help you through it. But this is not a proof-based class. This is a skills-based class. So for us, the important thing is that you get comfy using this. Dalton asks, since pi over 4 is finite, it's convergent. Yeah, so because that integral comes out to a finite value, that integral must converge, right? And since the integral converges and the function is positive, continuous, and decreasing, the series must converge as well. So yeah, remember what it means for an integral to converge, right? This is kind of a big deal. Our new thing is series, but here we relate a series to an integral. And so you have to remember not just what it means for a series to converge, but also what it means for the integral to converge. Yeah, what it means for this integral to converge is that this limit is finite, right? This limit exists and is finite. Here, that limit is pi over 4. Pi over 4 is definitely a number. It exists and is finite, right? It's like a little bit smaller than 1. So yeah, so because pi over 4 is finite, the integral converges. And then by the integral test, since the integral converges, the series converges. Ryan asks an interesting question in chat. What about the other way around? If I knew that the series converged, could I conclude that the integral converges? Yep. So if you somehow knew that this series converged ahead of time, you could conclude that this integral converges. Also, if you found that this integral diverged, then you would know that the series diverged. So what the integral test says is that under those hypotheses, positive, continuous, decreasing, the series and integral do the same thing. So whatever you find one to do, the other does as well. And usually the way we use it is we compute the integral and then say the series does the same thing as the integral. Because we're good at integrals, because that's what we spent the first third of the class on. Bueno? Good, good. All right. So we're ready for another theorem then. You may remember we had a family of integrals called P integrals. Improper type 1 integrals of the form integral a to infinity 1 over x to the p dx are called P integrals. P integrals converge if p is strictly bigger than 1 and diverge if p is less than or equal to 1. So what we're going to do now is relate those P integrals to a special family of series. I'm going to get some water. Oh, do I have water here? No. All right, yeah, I'm going to get some water. I'll be right back. All right. Theorem. Series of the form sigma n from wherever to infinity, 1 over n to the p, are called p-series. P-series converge if p is bigger than 1 and diverge if p is less than or equal to 1. You can imagine how we're going to prove this theorem. We're going to use the integral test to relate a series like this back to an integral like that. So I will prove this for you. This is an easy proof. Let S be sigma n from a to infinity, 1 over n to the p. Use the integral test. So the integral test, and I'll abbreviate that IT, and you should always do this, right? You'll notice every time I use a convergence test, I write down the name of the convergence test here, and then write out the statement of the test. That's important. That lets your reader know what the fuck it is you're doing. Without that, your work will look very confusing. So here, an is 1 over n to the p. So f of x is 1 over x to the p. F of x is positive, continuous, and decreasing. Positive for all x greater than 0, right? Because x to the p is guaranteed greater than 0 if x is greater than 0. Continuous for all x not equal to 0, because 1 over x to the p is rational. So continuous everywhere except where the bottom is 0. And decreasing because 1 over x to the p is the reciprocal of the increasing function x to the p, right? So we get positive, continuous, and decreasing pretty easily. This function has to be positive if you feed it positive x's. I mean, depending on the power p here, it might be positive even for negative values of x, but I'm only interested in positive values of x because my sum is running over like 1 to infinity or 0 to infinity, something like that. So yeah, this is definitely a positive function. It's continuous as long as the bottom isn't 0. The bottom is only 0 when x is equal to 0, and I'm definitely not interested in x being 0 for the series, or n being 0 for the series. And decreasing because it's the reciprocal of an increasing function. Straight power functions are always increasing functions as long as that power is positive. So the series sigma n from wherever to infinity, 1 over x to the p, converges or diverges together with integral a to infinity 1 over x to the p dx. However, integral a to infinity 1 over x to the p dx is a p integral. So it converges if p is bigger than 1, and diverges if p is less than or equal to 1. Thus, by the integral test, sigma n from wherever to infinity, 1 over n to the p, converges for p greater than 1, and diverges for p less than or equal to 1. Yeah, Morgan, that's what it says for 2. Yeah, that's correct. So 2 says continuous for all x not equal to 0 because 1 over x to the p is a rational function, and rational functions are continuous everywhere except where the bottom is 0. So in other words, this function is discontinuous only at x equals 0. But I'm not interested in x equals 0. My sum is going to run from like 1 to infinity or 2 to infinity, something like that. So the values of x that I'm considering here are the same as the values of n that I'm considering here. And the values of n that I'm considering here are all positive, all bigger than 0. So 0 is not in the range of summation. So this function is continuous everywhere I care about. So in other words here, a, the number little a that you see me writing all over the place as the lower bound for this sum, a here is assumed to be a positive number. So I'll make a note here. A is an arbitrary positive integer. So I'm using a as the lower bound here instead of 1, just so that you can say, oh, well, it doesn't matter where the series or integral starts, as long as it starts at some positive number. So this is a type 1 integral and not a type 2 integral. I can hang out on this page for just a second longer in case you have any questions or things you want to look at. So a is a positive integer. The series of the form sigma n equals a to infinity 1 over n to the p is called a p-series. And p-series converge if and only if p is bigger than 1. That's the theorem. The proof of the theorem starts by letting S be a p-series. So sum from a to infinity 1 over n to the p. If you don't like all of these little a's, you can just replace them with 1 everywhere. So sum 1 to infinity 1 over n to the p. We're going to use the integral test. The integral test says, take this guy, swap the n's for x's. That's your function. Check whether that guy is positive, continuous, and decreasing. He's positive for all x greater than 0 because he's the reciprocal of a positive function. Right? It's 1 over something, and that something is positive, so it is positive. He's continuous everywhere except at 0 because he's a rational function, and rational functions are continuous everywhere except where the bottom is equal to 0. And he's decreasing because it's the reciprocal of an increasing function. So in other words, I'm checking here that we are positive, continuous, and decreasing on the interval a to infinity, where a is an arbitrary positive integer. So as long as these things are true on this interval, then the integral test will work. And these things are true. Therefore, the series converges or diverges together with this integral. Oh, did I write an x here? I'm sorry. Here, please fix this. I goofed here, a little typo. The series here should be 1 over n to the p. So the series sigma 1 over n to the p converges or diverges together with the integral 1 over x to the p. But the integral 1 over x to the p is a p integral. So we know when he converges. He converges if p is bigger than 1 and diverges if p is less than or equal to 1. Therefore, by the integral test, my series converges if p is bigger than 1 and diverges if p is less than or equal to 1. So Morgan asks a good question here. Do I recommend trying this after TFD? Kinda. Much like in chapter 7, where I gave you a bunch of techniques and then we had a section at the end to discuss strategies. Chapter 11, I will give you a bunch of techniques and then at the end we'll discuss strategies. Integral test is not usually my second stop. TFD usually is my first stop. So usually I'll try TFD first. If TFD is inconclusive, then I'll move on to something else. But there's a couple other convergence tests that I'll usually try before I resort to the integral test. Because this step here, showing that the function is positive, continuous, and decreasing, can be very time consuming. So on a test, I would usually go for like a comparison test or a limit comparison test, or maybe even a root or ratio test before doing the integral test. But you don't know what those are yet. We haven't talked about those yet. So for right now, yeah, if something doesn't fall to TFD, your next step will be the integral test. But down the line, you'll have other things that you'll probably want to try before the integral test. Other questions on this? Okay, then I'm going to move on. Let's solve a few problems. All right. So Ryan asked me a good question privately in the chat that I want to come back here and address. This item, showing that that function is decreasing, how would you do that? By taking a derivative. Well, the problem here is that we don't know what p is. I'm trying to prove a theorem that says if p is greater than 1, the series converges. If p is less than or equal to 1, the series diverges. So if you wanted to come to this step and show that this is a decreasing function by taking a derivative, you would have to split up into a few different cases. You would have to show that this function is decreasing if p is bigger than 1. Then you could separately show that this function is decreasing if p is between 0 and 1. And then you could separately argue what happens if p is less than 0. So this step with the derivative is a little bit nasty. In fact, it depends on whether p is bigger or smaller than 0. I kind of brushed it under the rug here, but if p is negative, then this is not an increasing function. Then this is not a decreasing function. If p is negative, then we would have to step outside and use TFD. So I'm being a little bit lazy there, but I think if I read Ryan's question correctly, derivative to show that it's decreasing for p integral, do we just say that the series converges if p is greater than 1? We're trying to conclude that the series converges if p is greater than 1, but to show that that function is decreasing using the derivative, you would have to show that the derivative is negative. And that would require breaking up into cases. Okay, so let's come back here. The series S, does it converge or diverge? Good, TFD is inconclusive. In fact, TFD is inconclusive on all of these. That's by design. We could use the integral test if we wanted to, but it's a P series. This is a P series with P equal to 1, yeah. Since P is not less than 1, the series diverges. Good, yeah, exactly, yep. So this is a neat example. This series actually has a name. It's called the harmonic series. And even though it's divergent, mathematicians love this series. The sequence 1 over n is a convergent sequence, but the series sigma 1 over n is a divergent. Oh shit, yeah. Since p is not greater than 1, thank you. Yeah, good catch. Fernando said, caught that there, yeah. So since p is not greater than 1, the series diverges. Sorry about that. So this is a divergent series on which TFD is inconclusive. This is a good example series to keep straight in your mind the rules for TFD. TFD says if the limit of the ANs is not 0, then the series diverges. People always want to go the other way and say if the limit is 0, then the series converges. Here is a great example of a series where the limit is 0. If you send n to infinity, 1 over n does go to 0, but this series diverges. Correct. Dalton asks, so we don't need to check for positivity, continuity, and decreasing? No. I have my theorem on P series. So as soon as I can say, oh, it's a P series, then I can tell you right away whether the series converges or not. If P is bigger than 1, series converges. If P is less than or equal to 1, series diverges. So since, yeah, it's nice. It is a little bit OP. There's a lot of shit you can do with this. In other words, just like P integrals formed a really nice basis for comparison with the integral test, or sorry, with improper integrals, P series form a nice basis for comparison with infinite series. So it's a large family of series about which we know everything. So they're really good to compare other series to. And I'll give you the comparison test next week. But for now, we just want to get comfy with these. All right, what about T? T is not quite a P series, but if you bring the 2 outside, this is a multiple. This is a constant multiple of a P series. In other words, this piece, this is a P series. And here P is equal to the square root of 2, which is bigger than 1, right? This is about 1.4. So the series converges. R, let me take the work for R down here. That's sigma n from 1 to infinity 1 over e to the n plus sigma n from 1 to infinity 1 over n squared. So R is definitely not a p-series, but it is a sum of two series, one of which is a p-series, the other of which is geometric. This is 1 over e all to the n, and this is just 1 over n squared. This is a p-series with p equal to 2, which is bigger than 1. Therefore, sigma n from 1 to infinity 1 over n squared converges. This is a geometric series. With common ratio r equal to 1 over e. So the absolute value of r is the absolute value of 1 over e is 1 over e, which is about 1/3, which is definitely smaller than 1. Therefore, he converges. So R is made up of two series, this guy plus this guy, each of which converges, since R is the sum of two convergent series. R itself is convergent. So the series R converges. Q is not a p-series because it's not just 1 over n to the p. So I want to look at Q now. Because of the n plus 1 downstairs rather than just n, this is not a p-series. However, you can do something neat in infinite series called index shifting. Check this shit out. It's just like making a u sub, only I'm doing it in a series. Remember, I say series and integrals are very, very similar. The integral test shows us just how similar they are. Well, here I'm going to show you a little bit more. If I let k be n plus 1, then k minus 1 is equal to n. I also have to change my bounds. When n is equal to 3, k is equal to 4. When n is equal to infinity, k is equal to infinity. And if I make this little u sub called an index shift, then I see that Q is the same as the series sigma k equals 4 to infinity 1 over k squared. That is a p-series. With p equal to 2, which is bigger than 1. So the series Q converges. Index shifting is something that's going to become more important as we work deeper and deeper into chapter 11. It's not the only way to do this. And the part that usually fries people's brains is that now I could actually come back and write this as sigma n equals 4 to infinity 1 over n squared. Because there's nothing special about the symbol k. So we can index shift this. This is an index shifted p-series, and I can shift the index back to make it look like a p-series. And then if you want to, you can swap the k's back with n's. It really doesn't matter. All right, so these are some fun examples of things that we can do now that we know about p-series that we couldn't do before, and we can do them fast. You could do all this with the integral test, but it would take forever. Down here it says the absolute value of r is the absolute value of 1 over e is 1 over e, and that's approximately 1/3. 1 over e is like 1 over 2.7, right? 2.7 is pretty close to 3. So I'm just approximating. I'm just using this to explain to you why 1 over e is smaller than 1. Well, remember the rule for geometric series. So our memories need to be sharp. A geometric series will converge if and only if the common ratio has absolute value less than 1. So here, this piece, which is the piece of r which is geometric, has a common ratio of 1 over e. The absolute value of 1 over e is less than 1. I mean, I can give you a more exact approximation. Pretty close to 1/3, right? 1 over e is like 0.36. So 1 over e is the absolute value of the common ratio, and that is less than 1. Since the absolute value of the common ratio is less than 1, the series converges. So not all of r, just this piece of r converges because it is geometric and the common ratio is small enough. That's the idea. And then if you add up two convergent series, the result will be convergent. Right? Finite plus finite is finite. Okay. So I think we should have a reasonable feel for the integral test and comfy with the idea of what p-series are. I want to kind of recap some rules from 11.2 and 11.3 just to make sure we've said everything we need to say. If you add two convergent series, the result is another convergent series. Correct, Simon. Yeah, for most of these questions, I only care whether the series converges or not. Finding the value of the series, much, much harder. When it comes to telescoping series and geometric series, we can find the value, but for pretty much everything else, we can't. So instead of worrying about the value of the series, for us right now, we're just worried about whether or not they converge. I will give you some tricks for estimating the value of series when we talk about the alternating series test, section 11.5. But for now, we just care about whether they converge or diverge. So facts, if you add up two convergent series, you get a convergent series. If you add a convergent series to a divergent series, what do you think happens? Will the result be convergent or divergent? Good. Dalton's correct. If you add a convergent series to a divergent series, the result will always be a divergent series. What about two divergent series? So if I add two series together, each of which is known to diverge, am I guaranteed to get another divergent series? Or is it possible that something else happens? Sorry, you're going to see a little bit of my breakfast here. Our intuition wants to say that a sum of two divergent series should be divergent. Well, that intuition is wrong. Could also converge. Yeah, it could go either way. You might wonder, how is that possible? I will remind you to think of indeterminate forms, like infinity minus infinity. Sometimes that's infinity, but sometimes it's 0. Sometimes it's 5. Sometimes it's pi. So for example, each of these is a divergent p-series, but if I add those bitches up, you get a convergent series. Now, of course, it doesn't always go this way. You could definitely add 2 divergent series and get a divergent series also. But if things cancel beautifully, if things cancel perfectly, 2 divergent series can cancel each other out to give you a convergent series. All right. Let's do 1 or 2 more examples like this. Got to be a good hard problem here. How about that? Oh, are we out of time? All right, Nick. So I'd like to do 1 or 2 more integral test problems here with you guys. Let's look at 24 from the textbook. How about this guy? The sum from 2 to infinity, n e to the minus n squared. We can try to run TFD. The limit as n goes to infinity of the ANs here is limit n goes to infinity, n e to the n squared. That looks like infinity times 0, because n goes to infinity, and e to the negative n squared goes to 0, because that's like e to the negative infinity. So I can rewrite this as lim n to infinity n over e to the n squared. That looks like infinity over infinity. So if I use L'Hopital's rule, I get 1 over 2n e to the n squared, which is 1 over infinity, which is 0. So TFD is inconclusive. All right, we are going to have to run a little bit over. I'm sorry for that, but I was busy making food, so we're going to go about 15 minutes more. So TFD doesn't help me here. The limit of the ANs is 0. So TFD is inconclusive. What I can do, since this definitely isn't a p-series, and it's not related to any p-series in any obvious way, my next step right now would be the integral test. So an is n e to the negative n squared. So f of x is x e to the negative x squared. And I want to check, is f of x positive, continuous, and decreasing on the interval 2 to infinity. Why 2 to infinity? Because my series starts at 2. Positive? Well, where is f of x greater than 0? F of x is greater than 0 if and only if x times e to the negative x squared is greater than 0. E to the negative x squared, this is the same as x over e to the x squared. E to the x squared is always positive. So this is true if and only if x is greater than 0, because exponentials are always positive. So my function is positive if and only if x is greater than 0, and I'm paying attention to the interval 2 to infinity. So is this true here? Yeah. So f of x is positive on 0 infinity, which includes two to infinity. Continuous? So we set our interval to the integral test based on the balance series. Yes, the interval that you're concerned about for the integral test comes from the bounds for the series. The integral that you're going to compute will be the integral from 2 to infinity. So you need to check that all these things are true over that range of x values from 2 to infinity. That's exactly true. That's why I was using that little a back when we talked about the integral test. Little a is the starting value. Continuous? Yeah. E to the negative x squared is a composite function of e to the x and x squared, both of which are continuous. So x e to the negative x squared is continuous because x and e to the negative x squared are both continuous everywhere. Right? So remember, you've got some rules from Calc 1. If you multiply two continuous functions, the result is continuous. So since x and e to the negative x squared are both continuous, so is their product. And e to the negative x squared is continuous because it is a composite function. So remember, if you have two functions that are both continuous and you compose them, you plug one into the other, then the result is always continuous. So the composite e to the negative x squared is continuous because it is a composite of two continuous functions. And x e to the negative x squared is continuous because this piece is continuous and this piece is continuous. And the product of two continuous functions are continuous. So yeah, this function is continuous not just on 2 to infinity, but everywhere. Decreasing. This is where we have to do some work. F of x is x e to the negative x squared. So f primed of x this is a product rule derivative, will be e to the negative x squared plus x times negative 2x e to the negative x squared. So just using the product and chain rules there to get f primed. I can simplify this. F primed is therefore, I'll factor the e to the negative x squared out. And what I get is 1 minus 2x squared which is e to the negative x squared times 1 minus root 2x times 1 plus root 2x. You make a number line for f primed. The two roots here, this guy doesn't continue, isn't ever 0. This guy is 0 at 1 over root 2. This guy is 0 at negative 1 over root 2. And if you plug 0 in here, this piece is 1, this piece is 1, this piece is 1. So f primed is positive here, and therefore negative here and here, because each of these are multiplicity 1 factors. So f primed is less than 0 for all x's bigger than 1 over the square root of 2. Therefore, f itself is decreasing for all x's bigger than 1 over root 2. In particular, f of x is decreasing everywhere on the interval 2 to infinity, because 1 over root 2 is smaller than 2. So positive continuous decreasing, check, all good. This is your standard decreasing argument. Take the derivative, figure out where the derivative is negative and positive. Anywhere the derivative is negative, your function will be decreasing. Since this set is contains this set, I know that my function is definitely decreasing everywhere on this set, which is the set I'm worried about. All right, thus, by the integral test, the series sigma n from 2 to infinity n times e to the negative n squared converges or diverges together with the integral 2 to infinity x e to the negative x squared dx. So now I need to compute that integral. If that integral converges, my series converges. If that integral diverges, my series diverges. So now we compute integral 2 to infinity x e to the negative x squared dx, which is the limit as r goes to infinity, integral 2 to r, x e to the negative x squared dx. I'm going to make the substitution z equals x squared. dz is then 2x dx. My bounds will change. When x is equal to 2, z will be equal to 4. When x is equal to r, z will be equal to r squared. And I get that this integral is the same as lim r to infinity, 2x dx. Here's x dx, so I'll have a 1/2 pop out, integral 4 to r squared, e to the negative z dz. An antiderivative for which is easy to find. I'll bring the 1/2 all the way out front. Then I have lim r to infinity e to the negative z has antiderivative negative e to the negative z, and I evaluate from 4 to r squared. This gives me 1/2 lim r to infinity e to the negative 4. What is that? Minus e to the negative r squared. So I do the evaluation and then I change the order of subtraction to make it look prettier. But you could write it as negative e to the negative r squared minus negative e to the negative 4 if you preferred. So this is 1/2 lim r to infinity e to the negative 4 minus 1 over e to the r squared. As r goes to infinity, r squared goes to infinity. E to the infinity is infinity, so this is 1/2 e to the negative 4 minus 1 over infinity, which is 0, so that's 1/2 e to the negative 4. So integral 2 to infinity x e to the negative x squared dx converges. Hence, by the integral test, the series sigma n from 2 to infinity n e to the negative n squared converges also. And you notice, sorry. And you notice I've been writing these blocks at the end of these problems. This is called a tombstone, and it's how mathematicians conclude a proof. So what you're doing when you run through these integral tests or whatever convergence test and telling me that the series converges or the series diverges, you're writing a proof. Proof writing is probably new to most of you. So it's important that you practice the structure and the style. The logical flow is everything here. And this is the first time in the calc sequence where you're really required to master the logical flow of proof. So what I'm saying is don't skip writing the words. Now we compute. So this converges. Hence, by the integral test, this converges. 3 parallel lines. I've seen that before, people just doing like this. There's also this. Different notations for, yeah, QED works. That's Latin for quod erat demonstratum, or that which was to be shown. But the tombstone was popularized by Helmholtz in the 1960s, and that's what you'll see in most math books. So that's the notation I use. The big thing, though, is that you're getting comfy with the logic, right? Which requires knowing the theorems and the tests very well. You have to know the hypotheses, which are like the inputs to the theorem, and the conclusions, which are the outputs to the theorem. And I've seen people fuck up both in spectacular ways, right? So you can run through the integral test and do everything right, but then if you forget the conclusion at the end, you might write something that is false. Or if you forget the hypotheses, you might find yourself trying to apply the integral test to a function for which you cannot apply it. For example, this guy. So numbers 27 and 28 in 11.3 in the textbook are very good. They ask you, why can't you use the integral test on these? So you could jump in and start trying to compute the integrals here, but it wouldn't tell you anything about the series because for one reason or another, the integral test is not a valid attack for these. Either the corresponding function is not positive, not continuous, or not decreasing. If any one of those things fails, then you can't use the integral test. All right, I think this is a good place for us to leave it for today. The homework that I've set up for you is going to be due on Monday, and you should continue working on that, but I would advise you to do a little bit more. So I would advise you to come into the textbook here and look at some more of these problems. Read the section. All right, I don't know why, but for whatever reason, people think in a math class they're not expected to read. You are. You must. You really, really should. come here and read this shit. All right, it's gonna take a little bit of time and it's gonna say mostly the same things I've said, but it's gonna go into a little bit more detail. Read it slowly, read it with pencil and paper. Then go do the homework. And then after you do the homework, if you're not feeling 100% confident with everything, come in here and work some more problems. Okay, all of the problems from your homework will be here, but of course there's more problems here than I could put in a reasonable homework set. So you should come in and work a few extra problems after doing the homework if you want to get good at this stuff. Monday of next week, I'm going to show you the comparison tests. There's 2 of them. There's one called the direct comparison test, and then there's one called the limit comparison test. After that, we're going to talk about alternating series and the alternating series test. After that, we're going to talk about the root and ratio tests and what it means to be absolutely convergent. After that, we will be ready for exam 2. All right, so we're like 2.5 sections away from touching exam 2. Section 11.7 is a lot like 7.5. There's nothing new here, but you're gonna learn how to choose when to use each test. And then we'll be getting into 11.8, which is power series. That's exam 3 stuff. So please work very, very hard right now. It's important that you are done with the sequence homework, the 11.1 homework. If you are not, you need to finish that shit today. And then get grinding on homeworks 7 and 8. You should be close to done with 7, working on 8. That's where you ought to be right now. If you're not there, please put in the extra time now. That way it will not bite you in the ass on exam 2. Exam 2 is the killer in this class. Exam 2 and exam 3 both have hard content. I used to put power series on exam 2 also. People really hated that. So I moved it to exam 3. That splits up the hard material. Power series for most people is straight up the hardest part. But it's hard if and only if you're not good at this stuff. So get good at this stuff. Do well on exam 2. And that way power series won't be so scary on exam 3 and everything will work out okay. I'm going to switch over to my office hour now. So if there's anything else that you guys would like to talk about with me, you can meet me over there. Otherwise, I will see y'all on Monday when we start talking about the comparison tests. As always, if you need more time on anything, submit an extension request in WebAssign, I will grant it. But remember, you're in the thick of it now. This is the hard shit. So you need to be working extra hard, putting in 3-4 hours a day on your homework until you are all caught up and in really good shape. All right? If I don't see you in office hours, have a safe weekend, and I'll see you on Monday. All right? Bye, guys.